I'd like to go through a couple different examples of amplifier circuits just to emphasize the basic strategy that we're using to analyze these. This is just a very small subset of circuits that we can use, and obviously these same techniques can be used for a lot of different amplifier circuits. So the first is looking at what we call a difference amplifier, and you'll see why it's called that once we do the analysis. But remember, we're doing that analysis based on these two rules. So I plus and I minus, the currents going into this inverting input and non-inverting input of the op amp, are going to be 0, or I could also say that as the input impedance of the op amp is infinite. And the second rule is that negative feedback, which I do have in this case because I have that R2 resistor connected between V out and that inverting input, is going to imply that those two inputs are equal. My non-inverting input equals my inverting input. And based on that, I'm going to have a general approach for how I tackle these circuits. So I'm going to try to figure out what's going on at the positive, at the non-inverting input of the op amp, try to figure out what voltage that is, and then apply that voltage to the inverting input of the op amp, and then do some basic Ohm's law or KCL in this case, equations to determine what output is in terms of input. So let's start with that. We're trying to figure out what this V plus term is. Right? In this case, V plus is going to be defined by this voltage divider effectively with VI2. I have two inputs to this difference amplifier circuit. I have VI1 and VI2. I have one output VO. Right? But this is effectively creating a voltage divider with the VI2 input. And now that we've calculated what this voltage is, because I have negative feedback, I know that this is the same as this voltage right here. And so once I know this voltage, I can do my KCL, where I know that these two currents are equal because I know that I don't have any current going into the op amp because of the infinite impedance. So I can write that as VI1 minus that voltage right here, so I'm going to call that V plus, divided by R1 is going to be equal to that same V plus minus V out over R2. I can substitute in this expression for V plus, and that ultimately simplifies down to V out is going to be R2 over R1 times VI2 minus VI1. Right, so that comes from the analysis of this op amp circuit. And so I have the difference of my two inputs, hence the name difference amplifier, and some amplification associated with that difference. So R2 over R1 provides effectively a gain in the circuit. Now I want to be very clear that that's distinct from the internal open loop gain of the op amp. That was that very high number, AV is how we defined it, but that could be up to 1 million, say. So this gain is defined, this is a gain for the entire circuit, right? All of the resistors and everything attached to it as well. So in this case, we have an output with some gain and the difference of the inputs. And this is a great way to potentially measure a sensor with reference to some known value. So if I'm trying to measure a temperature, for example, and I have a known temperature that I'm measuring that with respect to, right, this would be a great circuit in which I could do that. Of course, this isn't a perfect circuit, right? If I put a sensor that I connect up to VI2, the input impedance that would see, right, is basically the sum of these two resistances, R1 and R2. So if I choose those as a couple kilo ohms, that wouldn't be a very high input impedance for this amplifier circuit. And the same thing can be seen on this input here as well. So if I wanted to hook that up to some kind of voltage divider that I've used to measure a resistive sensor, so maybe this is a thermistor, maybe it's a light sensitive resistor, and I have an R naught here, and so I have this set up so that, you know, when this is R naught, right, I should get 0 at the output, but as this sense resistor changes, I'll get a different input there. But because I have this, you know, potentially small input impedance, I can have some pretty significant loading on this circuit, right? Depending on what this nominal resistance is, this R0 is here. So instead we can suggest a better option. Instead of just having a single op-amp circuit, I can use multiple op-amp circuits to accomplish what I'm trying to do. So in this case, I still have my difference amplifier here, but now to prevent the problems that come with having a potentially small input impedance to that difference amplifier circuit, I also have some unity gain buffers as effectively an isolation layer for my circuit. And this entire thing can actually have a name, and this is one version of what we would call an instrumentation amplifier. And you can actually buy chips that are instrumentation amplifiers that do all of this for you, and some of them have even more levels of op-amp to give you even more amplification potentially for a sense signal. So in this case, it doesn't matter what I'm hooking up because I know I have this unity gain buffer at the start, and so I don't have to worry about input impedance or output impedance of my sensor. To show one more example of how we might use an op-amp in an amplifier circuit, let's look at DC offset. So oftentimes if I'm measuring some signal, and maybe this is some voltage over time that's coming from my sensor, I might have in this a DC offset right here, and remember that's the mean value of that signal. And oftentimes I don't really care about that DC offset. That DC voltage is something that's an artifact of how the sensor is designed. What I really care about is the AC component of that signal. So the problem that I have if I hook this up to a standard kind of inverting amplifier topology is that if I have, say this DC offset is somewhere on the order of 3 volts here, right? And the small AC component that I'm trying to amplify, right? That's the signal ultimately that I'm interested in. That's only varying something like a couple millivolts, right? So I need a fair amount of gain out of this, so say maybe 10 to 1 or 100 to 1 gain, right? But by the time I've done that, even if I do a 10 to 1 gain, what I'm really amplifying is that 3 volt DC offset as well. And remember, this has that power supply associated with it, where I have a positive rail and a negative rail on that. And so if I amplify this, I'm just going to saturate the signal at the output, right? This is just going to look like VDD or something close to VDD at the output. I'm not going to see this variation in the output. So what I want to do is effectively remove the DC offset. So now make this centered around 0 volts instead of around 3 volts. And then I'll only amplify the portion of the signal that I'm interested in reading. And a great way to rid ourselves of this DC offset is to realize that there's nothing magic about this virtual ground in a basic inverting amplifier. So I've hooked up ground to my non-inverting input. That effectively makes a virtual ground at the inverting input, and so I can do my math based on that and find out my amplification, right? But instead of putting ground here, I can put another voltage there instead. And so maybe this is R3 and R4, and I've defined that R3 and R4 so that this is approximately the 3 volts that I had, or I should better write that as kind of the DC offset that I want to remove. So I'm going to call this Vref, and I generally want my Vref to be equal to the DC offset to be removed before I amplify things. So let's go through the analysis of this. So I have a negative feedback configuration, which means that I'm also going to have Vref at this input. And so then I can do my KCL on that. So Vi minus Vref over R1 is going to equal Vref minus Vout over R2. So I can find a Vout is going to equal a negative R2 over R1 times Vi minus Vref plus Vref. Now this term right here is what is removing my DC offset. That Vref term is getting subtracted from my input. So if I had a 3 volt DC offset Now this term will be centered around 0, and that is what is receiving my amplification of R2 over R1. And then at the end, in the output, that also gets added back in, so that original DC offset gets added back into my signal, but now that the signal that I'm interested in is the part that's amplified, not the DC offset part. Let's do one more analysis of an op-amp circuit where instead of just looking at resistances in our analysis, we're looking at capacitances as well. And the short answer as to how we're going to do this is exactly the same way, but instead of thinking of resistances, I'm going to think of impedances. And a capacitor or inductor would just show up as a complex impedance. So this term right here, the impedance of this is going to be 1 over j omega c. At high frequencies, this looks like a short. At DC, it's blocking current. I'm going to analyze that the exact same way. I try to figure out what voltage I have at my inverting input, in this case ground. So I'm going to have that same voltage at my non-inverting input because I do have negative feedback. In this case, it's through a capacitor, it's through a complex impedance. But I do have a connection between V0 and that non-inverting input. So I have a virtual ground right here. And then I can apply KCL, where I'm looking at these two currents because the current going into that op-amp is going to be 0. So in this case, VI minus ground, right, because this voltage is ground since the inverting input is ground, over R is going to be equal to 0 minus V out over, in this case, I'm using this complex impedance ZC. That gives me a V out of minus ZC over R times VI. So it's my standard inverting amplifier configuration, but in this case, it's not just resistances, I have a complex amplification. And if I substitute this value in here for that complex impedance, I'm going to get minus 1 over j omega RC times Vin. This is in the frequency domain, right? I'm looking at an omega term here. If I want to look at this in the time domain, so VO with respect to time, now I have to remember that a 1 over j omega term is effectively equal to an integration. In this case, my output voltage is going to be minus 1 over RC, the integral of VIT dt. So this is often referred to as an integrator circuit. Now, a really interesting application of this particular circuit to a sensor is looking at piezoelectric sensors. These piezoelectric sensors, which are quite common, it's just another transduction method. We talked about changing resistance, changing capacitance. Piezoelectric sensors rely on a particular type of material that are going to generate a charge based on some stress or strain applied to the material. So it's going to generate a charge proportional to a displacement. And so these are used in accelerometers, force sensors, pressure sensors, all of those good things. So I could write that as I'll get an input voltage that is R dq dt from that sensor, where Q is the charge based on that sensor. So my V out in this case is going to be minus 1 over RC times R integral of dq dt times dt. My r's are going to cancel, and I'm just going to end up with minus 1 over c times q of t. So this circuit is also used, in addition to a basic integrator, as a charge amplifier, which is highly relevant for things like piezoelectric sensors.